Welcome to the Geological Society of the Oregon Country monthly meetup. We are the oldest collaboration of amateurs and professional geologists in the Pacific Northwest. You don't have to be a member to attend this meetup, and you don't have to be a member to attend our lectures. Membership is required for our field trips, which hopefully we will start again this year coming up. We're going to have a few announcements, and then Andrew Dunning is going to present the geology news, and then we're going to have a discussion about what we've learned or haven't learned about earthquake preparedness from our experiences in the last couple of weeks with the ice storm. So actually, I'm going to start. Sheila, if you want to tell us what some of the upcoming lectures are, we'd be interested to hear what we can expect later in, I guess, the month of March now we're looking at.
Okay, so coming up in March, which is just a couple weeks from now, we will have Carrie Gordon will be our speaker, and she will talk to us about the central volcanics. It's going to be related to our field trip that we're going to have out there. And so she lives in the Prineville area and worked for the Forest Service for her career. And she's going to give us an overview of the geology of that portion of Central Oregon. In the next month after that, we're going to have Bruce Bjornstad, and he's going to talk to us about his new book, which he's got drone pictures of the pathway of the Missoula floods and its changes on the landscape. So get ready for a lot of beautiful pictures, and that'll be our April meeting. Our May, we'll have John Major from USGS, the Cascade Volcanic Observatory, and he's going to tell us about the dangers of volcanics in the Pacific Northwest and what the role of the Cascade Volcanic Observatory is. And they're basically, for those of you who might not know what they are, they're in charge of monitoring all our volcanoes, because we're living in an area that has active volcanoes. And then I won't go on beyond then. Bill Orr is thinking of putting together another talk that's not set yet, but he always has fascinating talks. And that's all I know at this point yet.
That's great. I'm really looking forward to Carrie's lecture next second Friday evening of the month, and that'll be March.
And we meet every second Friday of the month. We do that, right? And now we're doing everything on Zoom.
Now we're doing everything on Zoom. Eventually, we will return to Kramer Hall 53 at Portland State in downtown Portland. But for now, we're on Zoom. So we would normally talk about field trips at this point. I don't see Carol Hassenberg, our field trip coordinator, and so we won't dwell on what the field trips are, except to say that, again, for members, you'll be getting emails that let you know what the field trip opportunities might be coming up in the next year.
Some of the folks in my breakout room were asking about field trips, and I know that Carol is putting together a survey to try to get make it as equitable as possible to try to get you on at least one field trip if you want to go. Good. Because we were thinking that we might be swamped with a lot of people.
And this year we aren't offering the usual public field trips that we have, the downtown field trip and some of the local east side field trips, but we'll offer those as soon as we can.
Okay, so those were canceled.
Those are all canceled for this year. You know, if we get an opening up, who knows, we might schedule one sort of at the drop of a hat, because I know a lot of us are going to want to get out there.
It's still a little unclear to me whether I'll be able to offer the helicopter tours of Mount St. Helens again, but hopefully I can, and there should be a lot of interest in that as well. Okay.
Thank you. I want to talk a little bit about the State Department of Geology and Mineral Industries. As some of you know, that was on the governor's chopping block, and then largely due to the efforts of our organization, and you really should give yourselves a hand, the efforts of Yume Wang, a member and former employee of Dogami, as well as Clark Neuendorp, who's a board member here, Sheila herself, our president, and Dr. Scott Burns and Chris Goldfinger, but especially our members. We've saved the agency. It was going to be divided into two agencies, and positions were going to be lost. But because of our letters that we wrote, our testimony that we gave, and the petition that we signed, which is still on our website, the agency will not be broken up. Now, it's still a question of how well it's going to be funded. And that's in the hands, it's in the hands of the legislature, as we say. If you have a legislator that you want to talk to, I met my senator last week, and that was an experience for me. Or if you want to continue to sign the petition, that's still relevant. We're hopeful that the core of the agency, especially the LIDAR consortium, will continue. And it looks actually like the LIDAR will be. Clark, do you have anything you want to add on that? Clark is a former employee of the agency.
I retired from Dagami after 19 years, and as one of my contacts still at the agency said, the amount of support and the I call it lobbying, but the efforts made by everybody was out. It was phenomenal. They had never seen this before. Legislators said that they were overwhelmed by the response, and the governor herself was shocked. And the governor is pretty much to blame for Dagami being put on the chopping block. So this was outstanding. Well done.
That's good feedback. I didn't know that we really made a difference.
Oh, absolutely. The response was just overwhelming for the legislators. They just couldn't understand it. They had never experienced that before.
We've shocked the governor, and I'm very proud of our president, Sheila Alston, for leading us in that effort in an era of increasingly fractious politics to find a bipartisan agenda that unites our members around a common mission. I think is a really valuable experience for all of us. And it's another way of showing that we can have influence in a state like this on those matters that arise from geology and concern us all. So I think we should pat ourselves on the back. The struggle is not over yet. There's still some funding issues, but we'll keep you informed of that.
So for those, Dagami's funding model is different from other state agencies. They are not 100% funded by general fund dollars, tax dollars. Dagami gets 30% of their operating budget from tax dollars. The remainder is from any other source that they can find, federal, state, local, grants, that sort of thing. So that's how they live. If there's a hiccup anywhere in that business model, the Dagami has no wiggle room, no financial cushion or anything like that. So that's why they struggle quite a bit.
And can I add that we are not a political organization, and we are not here, we would normally not do something like this, but in the face of the geologic hazards that Oregon faces, I just couldn't see that go down. The work of Dagami is, our danger here in the Pacific Northwest is unparalleled practically anywhere else in the world for earthquake and geologic hazards, landslides and so forth. And I just couldn't see us sit by without doing something to try to save. Dagami is the agency that's focusing on those geologic hazards, and we just can't afford to do without them.
And if you're interested in earthquakes, I think Bill Burgle has something to tell us about.
Yeah, this coming March 11th, which is the anniversary of the Fukushima earthquake, USGS, in conjunction with Oregon's Emergency Management Board, they're going to roll out something called Shake Alert. Now, Shake Alert is a program that basically takes advantage of the fact that when you have an earthquake, the earthquake itself sends out two types of waves. One's a pressure waves, and then one's basically a strain or a secondary wave, as they call it. And that's the one. The second wave is the one that does the damage. California put it online about 1.5 years ago, and now it's Oregon's turn. And then once we get ours up and running, then we're going to state of Washington is going to have theirs. I've got a 4-minute program. Paul, I can show it's a lot more explanatory than me if we got time.
I think we do, Bill. Yeah. Do you want to share your screen?
Okay.
Let me make sure I've made you a co-host.
Yeah. All right. Let me.
It's going to take you just a second here.
Yeah, I'm on there.
All right.
Is it showing up there?
We're seeing
Yes.
a black screen, and now we're seeing something. Yes, USGS. So we are seeing your screen, Bill. We're not hearing anything yet.
Not hearing anything?
When you share
is
the
there-
screen, make sure you share computer sound.
Okay. All right, hold on a second.
Yeah, go back, and when you share screen down in the lower left-hand corner, there's a checkbox for share computer sound.
All right. All right, so I'll go. So all right, so I do the meeting, right?
Bill, let's come back to you a little later in the program.
All right, that's fine.
Okay.
I'll figure this out.
Okay. Next up is our favorite grad student, Andrew Dunning from Portland State. I just learned this week what Andrew is going to be working on his master's thesis, and he might tell us a little bit about that. But Andrew is our geology journalist, and he does our geology news of the month. And I think his recap this month is going to be a little more encompassing, because we missed you last month, Andrew, because you were busy with grad student things. So Andrew, I think you are a co-host, and you can take it away.
All righty. I see Carol Hassenberg has joined. If you wanted to digress back to the field trips for a bit.
We might come back to that at the end. Thank you. Go ahead.
All right. Well, I will start my presentation here.
Now, as Andrew is doing the geology news, please feel free to put questions in the chat. Again, there are no stupid questions. These questions about what's a mineral, what's a feldspar, what's what's an earthquake, anything, please put it in the chat. Carol Miles will interrupt as is appropriate with a question. Or if you want to speak, we have we'd be comfortable with you just sort of raising your hand and interrupting. So what we want to make sure we have is a conversation.
Great. How's that looking? I can't tell if it's showing.
Looking
just
pretty good. You've got
Looking good.
there's a gray bar to the right of the screen, but
Oh,
maybe that's on purpose.
That's my Zoom.
Okay.
All right, well, that's okay. I don't need to see you. All right, this is the geology news. I'm catching up basically since December. We had a very geologically active couple of months here. Just a few days after our last meetup, a number of considerable and notable volcanic eruptions started, and I'm excited to get talking about those. Unfortunately, due to the, I've been working on my own research and a lot of other stuff associated with grad school, so I didn't quite dig into the new publications and research, even though Paul and Patty and Scott were very busy sending me news articles the whole time. So I'm just going to jump right in, and I'm going to start with sort of a 2020 year in review, because 2020 was a big year that had lots of interesting and fun things happening. I'm going to get the bad stuff out of the way first, and that's climate change. Permafrost is doing bad stuff up in Siberia. We finally got a good understanding. I didn't include it in this, but we finally have a good understanding of why those huge methane burst craters happen. You may have seen pictures of these huge craters coming up out of the tundra in Siberia, and we finally have a good mechanism for why that's happening, and that is ultimately climate change, melting permafrost and releasing methane, which then bursts its way through the soil. So 2020 was tied with 2016 as the warmest year ever recorded by modern temperature instruments, 1.84 degrees Fahrenheit above the 1950 to 1980 average. And part of the reason, if you're wondering that time interval is used, is because we have the most modern instrumentation for that time, and we know it is well outside the bounds of the Little Ice Age, which ended in the 1850s, but its effects were really seen through the early 20th century as well. And from a global, some of the effects of this warmth are rising ocean temperatures on average, which causes major currents like the Gulf Stream are weakened. It's now at its lowest strength in 1,000 years, which is verified through sediment cores and modern temperature logs and all sorts of things like that. And the Arctic Sea, all of the polar ice cap in the Arctic is melting rapidly, and that is spilling huge amounts of fresh water at a very low temperature into the North Atlantic, which is eventually going to interrupt the deep ocean water circulation. There's lots of research on that, and it's not all encouraging, but I'm going to push that to the side now and go to something that I like to talk about, which is earthquakes. Our biggest earthquake in 2020 was in Alaska on the Aleutian Trench on July 22nd, and that was a magnitude 7.8. That was a subduction zone earthquake. No tsunami happened. Very few people felt it because the Aleutian Islands obviously are very sparsely populated, and there was no tsunami, but it was within the subduction zone. The deadliest earthquake, unfortunately, was quite a bit smaller. It was a magnitude 7 in Turkey, and it also affected Greece on October 30th. There were ultimately 117 fatalities and over 1,000 injured, primarily due to collapsing buildings in the city of Izmir, and a few casualties also did result from a small tsunami in the Aegean Sea. Volcanoes. This was a great year if you were a volcano. The most exciting volcano that sort of started out the year was in the Philippines. Taal erupted on January 17th after more than 40 years of quiet. Ultimately, 250,000 people were evacuated, in which 38 people did unfortunately perish. However, they all perished in evacuation centers, and only one death is attributable to the volcanic eruption by itself. Philippine officials attribute most of these deaths to anxiety and heart attacks in evacuation centers because people didn't know what was going on. They didn't know what to expect from a major volcanic eruption. There were ultimately significant impacts to the local economy, totaling over $1 billion in the Philippine, I believe they use the Philippine peso, I don't remember their currency. And apparently a 500 meter high lava fountain blanketed the area in ash was observed. Here's a video showing the onset of that eruption. There was a crater lake inside the middle of the volcano. You can see as the lava rose up into this water-filled crater, it created this massive steam explosion. We call that a phreatomagmatic eruption. And this is one of the last things that this particular webcam recorded. This is the Philippine Volcanic and Seismologic Observatory. So this is the eruption as seen from space. That's the ash and steam cloud coming out of the volcano. Air traffic was significantly impacted in the South Pacific, and the only fourth order island in the world was destroyed by this eruption. What I mean by that is inside the crater lake, there was a small island. So you had an island in a lake, in an island in a lake, in the island of Luzon in the Pacific Ocean. And unfortunately, that island is no more. And now there's only a couple of third order islands, and those are in Canada, I believe.
Wow.
This shows the impact from the eruption. Crater Lake is gone. There's still some residual heat. And you can see the ash blanketing the island and the landscape. Really quite significant. Another fun volcano eruption in Italy from the most delicious volcano in the Mediterranean, Stromboli, which has been nearly continuously erupting for roughly 2,000 years and is recorded by Greeks and Romans and just about everyone else who has been around in the Mediterranean. There were several notable larger explosions in July at about 10 times the normal volume and size of explosions that are typical of Stromboli. And that's called a paroxysm, when one of these volcanoes has sort of a throat clearing eruption. Here's a fantastic video of one of these eruptions. I'm not going to play the whole thing, just a few minutes here so you get the idea. This is what it typically looks like. There's a little bit of glow, and then the main paroxysm. You get a large steam explosion because this magma is at depth interacting with the seawater. So you get these sort of bursts of these lava cinders, which then rain down and blanket over the volcano slopes. It's really quite beautiful to see, and this is a pretty fantastic video. And during the times of these explosions, it was doing this all day. Really quite something special.
Andrew, can we ask a couple questions about
Yes.
the kind of volcano, mafic, felsic, stratovolcano, whatever, that creates the phreatomagmatic explosion? And also, we have a question about, is there a village at the base of Stromboli?
Yes, there is a village at the base of Stromboli. You can see it here. No impacts are known from any of these eruptions. I wouldn't personally build my house on Stromboli, but clearly lots of people do. I believe these the volcanoes around the Mediterranean are primarily sort of mafic intermediate. They are subduction zone volcanoes as Africa collides with Europe and Eurasia. There is melt at depth, and we have a string of volcanoes through the Mediterranean. And a phreatomagmatic eruption is not dependent on chemistry. If you get any kind of lava interacting with water anywhere, you get a steam-driven explosion. Phreato meaning steam, I think in Greek. What was the other question? Did I cover all of them?
I think that was it.
Okay, great.
Oh, someone asked, was this filmed from water or from the village?
This video was on the upper slopes of the volcano. This is the summit right around here. Other videos you've seen, here, this one is in the suggested videos. That was taken in 2018, I believe, from a boat where a small pyroclastic flow came down off the summit. And here, I'll just play it because, oh, that's not working. We can come back to that another time, perhaps.
Okay.
Where did my presentation go? There we go. Can you still see it?
Yes.
Awesome. Etna. This is my favorite volcano of 2020, and it's ongoing today. There is another massive sort of paroxysm event. There's that word again, a few days ago. And I think this picture is from only the last week or so. Etna is one of the world's most active volcanoes, and it is the largest volcano in Europe. This photograph is taken from quite a distance away. This volcano is massive. I believe it's larger in volume than just about anything else we have in the Northwest. It's a massive mountain. And its normal state is sort of occasional belches of ash and cinders from the summit. But large lava fountaining and a lava flow event began on December 14th. This is one of those paroxysms, sort of a throat clearing. Etna cleared its throat and is now spewing and belching all sorts of stuff. This is I didn't catch the date from this one. This is a satellite picture. You can see the snowy upper slopes of Etna, and a lava flow is issuing from the summit. The largest paroxysm began on February 21st. This is pretty recent. Etna is so big. So even in all these pictures, you're going to see villages, but they are really quite far away from the summit, and activity rarely gets far from the summit area. So there's very little danger to the surrounding communities. Some of the photographs have just been stunning. I mean, look at this, the clear blue skies and the crystal clear nighttime skies, and the lava glow illuminating the ash and eruption cloud. Absolutely beautiful. Some of these lava fountains are truly gigantic too. This is easily 100 or 200 meters here.
The overall tectonics of this, is this also a subduction zone, sort of volcanic system like the Cascades, or is there something else going on here?
Yes, the tectonics there are a bit more complicated.
Yeah.
I don't understand it too well because I haven't looked into it that much, but ultimately it is subduction zone related. There's no hot spots or anything else going on. This is a very old subduction zone. It's the same one related to the Alps uplifting at depth. There's a lot of microplates and complex faulting, but ultimately these volcanoes are derived from the subducting African plate as it rolls northward into Europe.
And
Fantastic.
is there a site where you get these videos and stunning pictures?
Most of these pictures I grabbed off of Twitter. Volcano Twitter has been erupting with joy about the Etna activity, so to speak. I believe these videos I grabbed off of official websites. I don't remember exactly which. I just looked them up.
Our old friend Larry asks, are the Alps still uplifting?
Yes,
They are.
they are.
And that is that continent to continent collision, or is that part of the African plate?
The Mediterranean is oceanic crust. It's very old
Oh, okay.
oceanic crust, but it's also effectively accreting microplates and terrains onto Europe, much like we have in the Western US. That system is quite a lot more complex than ours is. Ours is a lot older. I mean, that's a very old system too, but the accretion is really still ongoing in Europe, is my understanding. So yes, the Alps are uplifting.
The Alps are uplifting. Good, good. I'm glad. Go Alps. Ellen asks, what is a paroxysm?
So that's, I'm not positive of the technical definition, but the best way to understand it is a throat clearing. So the volcano, it has its little conduit from the magma chamber to the summit of the volcano, and sometimes it'll sort of get clogged. Some magma might cool a little more, or there might be some fluid or gas interaction in there. But eventually it clears that, it clears its throat, it belches, and you get a much larger explosion because there's been some pressure built up at depth that forces its way out the summit. And that's what we saw in that Stromboli video. There was sort of minor, small activity, and then kaplooey, there was a much larger explosion, which was one of those paroxysms.
Good,
Basically,
good
yeah,
explanation.
basically a burst of activity.
Mhm.
Anything else?
That's
Before I
all we
move
got in
on?
the chat at the moment. Yeah, good questions.
Cool. All right, so if you remember our December meetup, I said,
I do.
so the USGS in Hawaii has detected a dike intrusion at the summit of Kilauea, a small, shallow lava intrusion into the summit of the volcano. Well, some more earthquakes followed, and then this happened. At the time the dike intrusion was detected, the USGS Volcano Observatory stated, we don't expect this to lead to an eruption because they detect, a half dozen dike intrusions per year and none of them lead to eruptions. This one, however, did. So you may remember that Hawaii had the Kilauea volcano in 2018. There was a flank eruption and the summit of the mountain collapsed and the lava lake drained and we had this huge crater. Well, it filled up with water. It was about 160 feet of water. And in a matter of hours, that lake evaporated. It completely boiled away. And some scientists who were on their overnight watch happened to look out the window and notice that there was an incandescent glow coming from the crater. And they said, well, that's funny. And they sent some guys out to check it out, or some scientists, I should say. Their gender is pretty diverse there at the Hawaiian Volcano Observatory. And they noticed, hey, the volcano's erupting. It hasn't done that for 2 years. So after a 2-year quiet period, Kilauea now has a lava lake back at the summit. And within a few days, it was over 300 feet deep. You can see here, this is the estimated lava lake depth in meters here. And this is the date. It started on December 21st. And by December 24th, it was over 160 meters. That's 400 or 500 feet. I'm not going to do that calculation right now. You can see the lava lake right here. And these are some of the earlier stages of the lava lake. This is the water lake, not the lava lake.
Do we have a burping or clearing throat analogy for the goddess Pele here?
No, it's a little bit different. This wasn't a throat clearing. This is more just lava moving its way up to the surface, which is what lava does. These are quite different systems. This lava has a lot less water in it, so it's less prone to explode.
So the column of steam in the previous image, that is not like with a rhyolitic felsic stratovolcano. That's not rock. Is that just steam from the lake, or is that also cinder and ash?
It's a little bit of both. Obviously, the rising lava was interacting with water, groundwater, and the lake. And it was also spewing gas. When lava reaches the surface, it releases a lot of pressure. Think of opening up a soda bottle and you get that. So there's a lot of gas, and in that gas, a lot of that is water vapor. And when that hits the surface, it does that. And also interacting with it, you did get a limited ash and cinders and stuff. They did collect samples of Pele's hair, which are these thin, wispy strands of effectively lava glass that were draped through the inside of Kilauea caldera.
Wow.
After the eruption. So yes, there was a limited amount of rock debris in that cloud, but it was not as much. There's effectively none now.
I was alluding to a difference in volcanoes that I probably sort of bungled the description of, but could you flesh that out for new members? The difference between what you'd see on Hawaii and what you'd see in a subduction zone.
A big difference in the Mediterranean volcanoes, because that's what I was talking about earlier. When oceanic crust, which is primarily heavy basalt and rocks like that, subducts and goes into the mantle, it carries a lot of water with it. And that water acts as a flux. That's the actual agent that causes melting in the wedge of mantle between the continent and the subducting plate. And in this little wedge here, you get a lot of water, and that rises and that causes melting in the mantle, which then is a little bit more evolved of a melt as it punches its way through the overriding continent in the Mediterranean Sea and creates volcanoes there. Excuse me. And just because those volcanoes are located in the ocean, their magma interacts with a lot of water. So you have a significant proportion of water in that melt dissolved, obviously as steam, and that impacts the eruption behavior. Up in the Northwest, we don't have as much water in our melt, very little, in fact, and that's just due to the way that the magma evolves as it rises through the crust. It's a little bit complicated for this setting to get too deep into that. I would have to get out my notebook from petrogenesis.
And Sheila comments that the higher the silica content of the magma, the more explosive it is. The
Yes.
silica makes it sticky.
Yes.
And
Yeah.
so the Hawaiian volcano is less sticky.
Yeah, this is really, really, really low silica content. This is in the order of, I believe, around 50% silica, whereas some of the volcanoes in the Mediterranean might be in that sort of 60%, upper 50s, lower 60% range. And here in the Cascades, we range from generally, depending on where you are, the bigger volcanoes have higher silica contents in the neighborhood of 65 to 80% silica.
That's a good explanation. So if you touch it, it won't feel sticky.
No, you would burn your finger.
All right.
Never,
Oh.
never touch it, Paul.
Never touch it.
Can I touch it?
No.
No? No. Okay.
So this is when daylight dawned on the summit lava lake at Kilauea. They have two vents erupting lava into the filling up this crater. This chunk here was actually an island. There's a few little smaller ones here. And we're not positive where that was derived from. It could have just been early material that was erupted and filled up the bottom of the crater. Would have been a little bit stickier because it would have been sitting around a lot longer before it got pushed out by the new magma, which is what you see now in this really dark color. And these were actually floating. These islands were floating around the lava lake for about a month before they eventually stabilized sort of over in this side of the lava lake, which is now over 700 feet deep. And to get you sort of a sense of scale, it's about 500 feet from where the lava is erupting to the bottom of the lava lake in this picture. The lava lake is about at this level right now. It's about 700 feet deep. So that's a lot of lava, and it is mostly liquid. I'll show another picture here. This is what it looks like. I believe this is this morning at the summit of Kilauea.
Lars asks, is the island floating?
Yeah, it was. It probably still is, but it hasn't moved for a long time. In the time-lapse videos, I should have included one of those. You could actually see it drifting around with the currents inside the lava lake. It was really quite something. I've never seen anything like it. And this is a time-lapse in infrared. That island is sort of anchored right here currently. Get that started. You can see little spillouts along the edge here. Even though the crust is all solidified in the east half of the lake here, this is where the new lava is erupting from the vent located about here and keeps churning up the crust in this part of the lake. It is all liquid underneath, which we know because it's spilling out around the crust, around the sides. But you could hypothetically walk around here and it would be perfectly okay. You would not be feeling so hot because of the carbon dioxide and sulfur dioxide, but it might be fun. I would enjoy that. Yeah, so now it's largely stagnant and half covered with lava crust. Any questions on Kilauea before I move on?
So you have a different sort of system here, but and maybe you've already answered this as best as scientists can answer it, but why this happens after 2 years? Is there some sort of recharge going on of the lower magma chambers? And we know this is over a hot spot, so it's a sort of different system.
Yeah. So since Hawaii is derived from a hot spot, it's in the middle of the Pacific Ocean. There's no subduction melting anything in the magma. So this is this hot spot is melted magma and heat derived directly from the sort of outer core and mantle boundary, and that is shooting up just like a blowtorch onto the bottom of the Pacific plate. And this magma, sort of the flow of magma from deep within the earth is pretty constant, we think. Maybe over a tens of millions of year time scale, it might waver a bit, but sort of on a year to year, decade to decade basis, it's constant. The 2018 event where the housing developments were buried by lava and there was all that dramatic lava flows and eruptions, that was a moderately large eruption for the system. So that drained the shallow magma chambers when all of that lava moved from the summit of the volcano and flowed out the side. So yes, that does recharge slowly over time. And that's why there was kind of a pause. It had to build up sufficient pressure to make its way back to the summit of the volcano between eruptions. Its neighboring volcano, Mauna Loa, is very similar in that it recharges slowly over time. Its last major eruption was in the 1980s. I want to say 1983. And since then, the volcano summit has been inflating ever since that eruption ceased, and that's because of the recharge of new magma into that shallow reservoir.
You've got some questions coming in. Actually, Carol, do you want to read the question? Carol Miles, do you want to read questions?
Yeah. So Larry is asking, how long might it take for 700-foot depth of lava to cool and solidify? Weeks or months, assuming no new lava is flowing in?
The Hawaiian Volcano Observatory released a statement to that because they were receiving many questions. I don't remember their exact estimate, but it was on the order of decades to centuries. I believe earlier lava lakes, they estimated weren't entirely cool until about 150 years later, because it's an enormous amount of material, very dense material, and it is heated, obviously very hot. I believe when this lava erupts, it's right around 2,000 degrees Celsius. So if you take, the math is, it's a big number, the amount of heat in joules that is sort of encased with this, and it takes a long time for that to dissipate. And obviously rock is a great insulator.
And Randall asks, has there been any correlated increase in activity regarding Loei? L-O-E-H-I? Sorry.
I'm not sure. I don't follow Loei too much. It's been a while since I've read too much about that. These two systems, the Kilauea Mauna Loa systems and the Loei systems, are effectively separate. I mean, they receive magma from the same source, but an eruption on Loei can operate regardless of any activity on the island of Hawaii.
That's a good question.
And Bonnie is wondering, are volcanoes only at hotspots and subduction zones?
That's a complicated answer to that question. Most of the time, yes. There are, I guess a better way to phrase that would be plate boundaries. Because you get rifting plate boundaries like you have in Africa or Iceland, and volcanoes erupt there because the crust is significantly thinner. And we see that here in North America in the Basin and Range, the Great Basin. So Nevada, Arizona, parts of California and Oregon, the volcanism is directly a result of the crust thinning. And as the crust thins, obviously magma, it causes the mantle material to rise, and that causes it to melt and pushes its way up through. There are a number of continental rifts where the tectonics is very complicated, but there is rifting in the center of the continent. You have this in New Mexico, the Rio Grande rift system, where again, the crust thins and magma rises and you get volcanoes. So yeah, hotspots, rift systems, and or plate boundaries. So subduction zones and rift zones. There's mostly three settings for volcanoes, and there are occasional outliers to that rule.
At least on this planet.
Yes.
You can also have tidally influenced volcanoes on Io, but those are the three
Yeah.
for us, it sounds
Those
like.
are the three for us.
Okay, good. Good, I'm glad that's all. I think
Anything
this-
else, Carol?
Just a couple comments that people could read on their own.
Okay. So I'm going to move on to January and February of this year. So that was just wrapping up 2020, and I've covered Kilauea and Etna now, and those are ongoing eruptions. So I'm just going to get the rest of the volcanoes out of the way. Here they are. There's 20 volcanoes with new eruptions or ongoing activity per the Global Volcanism Program. There's always other volcanoes under the ocean or in very remote areas, Antarctica, for example, some sort of Central Africa, where eruption is sort of continuous as long as records have been kept. And so they keep them off of this list. Erebus and Ngorongoro come to mind as some of those volcanoes. So these are ones with significant sort of unusual activity that they can classify as eruptions. In December, we had a roughly 2-month window in which there were no volcanoes erupting in Alaska, and that was the first time since the 1980s that has happened. But now we've got Semi-Sopochnoi, a Russian name for an Aleutian Island volcano. We don't know if it's erupting, but the seismometer has been recording activity, and a plane flight showed that there was ash on the snow. So, these volcanoes are very remote and very difficult to monitor. I'm going to move on to earthquakes now, which is, as I've mentioned before, my favorite thing to talk about. The biggest event in January and February was a magnitude 7.7 in the Loyalty Islands, and that is right here. Oops. Oh, well, that's down here. It's right here in the Loyalty Islands, which is apparently the name of an island change in the South Pacific. There was no tsunami. Interestingly, it was preceded by 2 magnitude 6 foreshocks. So the tectonics here are very complicated. It's there's a subduction zone, but it's the end area of a subduction zone where it sort of fizzles out, and there's some rifts in the area too. Very interesting tectonics down here in the South Pacific. There were several other magnitude 7s in Indonesia. Excuse me. That should read magnitude 6 in Indonesia. That was this one here, and in the Philippines here, magnitude 5 over here in looks like Western China, and then a magnitude 7 in Japan, right here. And right here is the city of Fukushima, which is very close to the epicenter of the 2011 Tohoku earthquake, which we are coming up hot on the 10th anniversary of. So this is a magnitude 7 aftershock of a 9.0 earthquake 10 years ago. And I really think that goes to show just how enormous the stress changes from an earthquake of that size, 9.0. This aftershock trail will go on for decades. And today, this morning, there was a magnitude 5 in Alaska. Very fun. Here is the western.
Andrew,
Oh, yeah.
got a question, and actually I was thinking it too. So this is a good example of, I didn't ask the question that I should have, and Anna has asked it, and I think Anna is one of our Reed students, one of our newest members from
Welcome.
the Environmental and Chemistry Geology 220 class there. Why do aftershocks happen, and how do we know that is an aftershock of that Tohoku earthquake?
So after an earthquake happens, the crust has sort of deformed in some way, and the way it deforms is highly dependent on the tectonic setting and the style of earthquake. But sort of those stress changes that happen just from the crust bending and flexing after an earthquake causes stress to change on other faults, and those faults tend to rupture. You can also have aftershocks along the same fault plane where, so during even a very large earthquake like a magnitude 9, the crust, the two rocks that are interfacing along the fault don't move homogeneously. They don't move in a perfect gradient radiating away from the epicenter. So the rest of the crust kind of needs to catch up to the main event. And the reason we're calling this one an aftershock is because it's in the same area as the big one, 9.0, the 3rd or 4th largest earthquake ever recorded. I believe that was really a planetary scale event. And aftershocks of this size. And the magnitude 7 that happened, it has an aftershock trail on its own that will go on for years.
And
Does that
then,
answer your question?
Sort of. I mean, so is it the physical proximity to the original epicenter, or is it just that it's part of the same general tectonic system? I mean, how do
Both.
you draw a line? Both. Okay.
Really both. There is some, there is fuzziness. Yes,
Mhm.
this could be an independent event, but just with the size of that magnitude 9, you can't ignore that.
Mhm.
There were parts of the slip at the very end of the fault where it reaches the subduction zone, where it reaches the sea floor. The Japanese measured approximately 150 meters of slip right at the sea floor there. So that means part of the crust moved 150 meters, roughly 470 feet in the span of the 10 minutes it took for that earthquake to happen.
Wow.
Just colossal amounts of energy involved in that.
and then how do you define something as a foreshock?
If it happens and then it is followed by a bigger earthquake.
Okay. Like within a close period of time?
Yeah, number of years.
Hmm.
The Earth doesn't subscribe to our measurements of time, so there's always a little bit of fuzziness in there.
Is that a question of, you can say it's a foreshock if the epicenter is in a similar spot, or is it
Yeah,
still,
or if it's
still a fuzzy
along-
thing?
Yeah, if it's within sort of a certain radius, like if an earthquake happened in Monterey Bay, and then a large earthquake happened near Point Reyes in California, you would not call the
Okay.
Santa Cruz earthquake a foreshock because it's too small and too far away.
We're coming up on our 1 o'clock hour in 15 minutes. And Andrew, I want to give you a little bit of time just because I heard your presentation on Wednesday. If you can tell us about your research briefly.
Yeah, I will.
But also if you need more time, let me know.
We are getting closer to the end of this.
Okay.
Just couple of more earthquakes I wanted to talk about that were very
We
interesting.
love the earthquakes.
Well, so do I. That's what I study. So this is the Western U.S. Last 30 days was the best visual I could get. And we have activity here, earthquakes in the Eastern California shear zone and Walker Lane. There were a few massive earthquakes here in 2019, a magnitude 7 and a couple of magnitude 6.5s, I believe. And there were half a dozen earthquakes felt in the San Andreas fault zone up here in the Bay Area and a couple down in this area. Last night, I believe around 1 a.m., there was a magnitude 4 off the coast of Oregon in the Blanco fracture zone. And this is where the Juan de Fuca plate and the Pacific plate are sliding past one another between the rift zones here and here. So as this spreads, that causes this to slide in the same sort of motion as the San Andreas fault. The continents are grinding past each other. Earthquakes there are quite common.
I love seeing that the earthquakes all around the traces of those faults. That's very cool.
It really highlights the clarity of the structures.
Denny has a question, which I'll let Carol read.
Oh, let's see. When part of a fault releases or there's a quake.
Oh, is it a question or is it an answer?
It may be
Question.
an answer.
It's a question.
It's a question. Okay.
Forgot the question mark.
When part of a fault releases, then for a time that portion is no longer bearing its share of regional stress. Perhaps this means that the unruptured segments of the fault are bearing any remaining stress all by themselves. Perhaps one or more will soon fail themselves as a result.
That's a rabbit hole, to say the least. Usually a fault's sort of influence is limited to one fault length in either direction. So in the Ridgecrest earthquake of 2019, I'm pulling this sort of out of the air here. I believe the fault length was about, the rupture in that earthquake was about 40 kilometers long. So there's an area roughly 40 kilometers on either side of that where we expect future earthquakes to be more likely for a time. But also because of the way that earthquake moved in the opposite direction, it is sort of clamping other faults together. Like when the San Andreas fault ruptured in 1906, it released a lot of stress sort of in this area, but it clamped together faults sort of in this area. I might have that backwards. I'm thinking of a diagram I looked at 6 months ago. So yes, it does release tension, which then can encourage earthquakes to happen, but then it also clamps faults closed and makes them less likely to generate an earthquake. Does that answer your question? It's
you.
quite complicated, difficult to distill.
Thank you.
Great. I'm going to talk about this little earthquake that we had in the Hood River Valley on February 9th. This is a little tectonic earthquake, obviously not related to the volcano. The volcano is pretty far away. Hood River Valley is a graben. So you have a fault here and another fault roughly here, which I helped dig a trench on. We studied over the end of this summer. And this earthquake could be related to either one of those structures at depth. It's pretty shallow. And I haven't done the math to find out which of these fault planes it's more likely to be on. But yes, this earthquake is related to the dropping down of the Hood River Valley.
Aha. Okay.
And this earthquake in Iceland, which was only a couple of days ago on February 24th, is very, very interesting. It ended up being a strike slip earthquake. It was a magnitude 5.7, which is large for Iceland. But the thing that sort of has Icelandic officials on high alert is the fact that the earthquake swarm and the aftershocks that are related to it are, this is a very large earthquake swarm, much more activity than is typical, and they've seen heightened activity at some of the nearby volcanoes and geothermal features. You can see here, this is called INSAR. This is from satellite. I believe it uses radar, and it shows that this area has moved away from the satellite 40 millimeters, and this area has moved towards the satellite 40 millimeters. So you can kind of see how the island of Iceland is moving there as a result of this earthquake. And that's all I have for this month. There was a lot of new research that Patty and others sent to me routinely, but I was focused on my own research this month. And
well, Andrew, tell us a little bit about that, because the grad students at PSU are doing some really fantastic stuff that's cutting edge. And I mean, it goes to a lot of these fundamental questions about the difference between subduction zones and hotspots. And so if you can talk a little bit about what you're doing and what's involved.
Here, let me stop my screen share here.
And I didn't give you a heads up on this. So if you don't have a slide, that's okay. But just if you can let us know.
I don't need a slide for that. So my own research, I'm studying under Dr. Ashley Strag, who has given talks for GSOC before. Back in sort of 2019, 2018, state geologist Ian Maiden, he's with Dogami, was looking at some recently acquired LiDAR data. So that's topography, which is derived from basically flying a laser on a plane over the landscape, and you get a really high resolution map without the vegetation on top. And he identified fault scarps. So when an earthquake happens and you get movement on the surface, you get a fault scarp. And he discovered some very young looking fault scarps out in the Strawberry Mountains in Eastern Oregon. I will just pull it up on Google Earth.
Yeah, because the strawberries are fascinating. The rest of Oregon is so geologically young, but you get out into the strawberries and boy, you got some pretty old stuff out there.
Yes. I can talk to that a little bit too. Or should I just share my proposal presentation?
Sure. We've got a couple minutes and you've got some really great information there. So
I won't get too into it because it's rather technical.
If there's geochemistry, you can kind of gloss over that.
There's no geochemistry.
Okay,
I'm not a geochemist. I learned that when I took petrogenesis, that I am not a geochemist.
I think we have some chemists in the room. So it's not that everyone is allergic to geochemistry, but
I'm not allergic to it. I just would
see,
rather talk about faults. Okay, so here's my project title. I'm evaluating the slip history and Holocene activity of faults in the Strawberry Mountains.
What's Holocene?
Holocene is the last 12,000 years.
Okay, thank you.
Okay, so this is the picture, an adapted version of the figure that I submitted for a lot of my grants and my final proposals. So the Strawberry Mountains are in Eastern Oregon, way out here. It's exactly 600 miles, 300 miles each way from my house. So that's a nice round number. And in this area, we have sort of these two fault zones. There's an east-west trending series of scarps up here, and then a north-south series of scarps down here. And nobody has expected active faults in this area. And the reason for that is because of, if you look at the GPS measurements for the area, these are actual GPS stations that are permanent, and they're continuously taking measurements of their position. And we see that there's sort of this crustal rotation going on. I believe this is probably pretty well known, and there's a lot of information about it online.
It
But
bears
there's very
repeating.
low.
It bears repeating for newcomers. The entire state of Oregon and Washington is rotating at a terrifying rate of, what is it, Andrew?
This is, I believe, 1 degree per 20 million years.
Okay. So that's measured there by the GPS.
Yes. And these vectors are, it's about 10 millimeters per year. So up here, you get the Olympic Mountains are moving roughly 20 millimeters a year closer to Seattle.
Mm.
But anyway, down here in the Blue Mountains area, there's very low internal strain. Up here, the big arrows mean a lot of internal strain, small areas, very little. So finding active faults in this area is a bit surprising. And it's a long-lived structure because you got 40-million-year-old volcanics faulted against 30-million-year-old volcanics. So something's going on here. And I think my research is going to figure out if these are reactivated faults from, so the Strawberry Mountains initially uplifted sort of between 30 million and 20 million years ago was their primary period of uplift initially. Since then, there's been some other uplift, but the uplift history is poorly understood. I'm going to zoom into the fault scarp here. You can see right here, this is the fault scarps. This is what we've been following across the landscape. There's a nice faulted terrace there, some other stuff. Check out this. This is a glacial moraine here, which turns up beautifully in this data set. This was deposited by a glacier, probably from the last ice age, but it could be a lot older, could be 100 or 200,000 years old. This is what we're going to study. There's no glacial chronology data for this area. We have no idea how old these glacial features are. But this fault scarp is very persistent. It's very clear all through the Strawberry Mountains. Let me go back to this overview. All of these are just ones I've mapped. There's others in the area. And so this is what I'm studying. How long ago did this earthquake happen? This fault, this scarp could be one earthquake, it could be two. Based on the way it looks, I think it's one earthquake, which makes sense based on some of the other parameters. And we're going to find out how long ago did this happen. We want to find out why it's happening. Why are there earthquakes in this allegedly stable block of the Blue Mountains? And if you have looked at the seismic hazard maps for the area, this is not going to be a significant component of my research. But this part, the John Day Valley and a lot of the Blue Mountains, is in the green zone that reflects a very low seismic hazard. But we've got obviously a recent earthquake in this area. So I think down the line, the next 5 to 10 years, I hope that will be revised by other researchers.
Yeah, Andrew, so how do you, so the scarp cuts through the moraine? Is that what you're saying? So
Yes.
So we know it's younger than, if the moraine was deposited at the last ice age, then we know that the earthquake happened more recently.
Exactly. And I think this is another glacial moraine here. I think this is last glacial maximum and the fault cuts that. So it's definitely in the last 12,000 years.
Okay.
It actually, a lot of it is pretty young and pretty well preserved. I would not be surprised if it is in the 2,000 to 3,000 year range. And that sounds like a long time, but for earthquakes, we generally say anything younger than 10,000 years is potentially active.
What methods are you going to be using both in the field and then back in the lab?
I'm going to be using a variety of methods. So the whole time at home, I've been measuring this fault, mapping some of the geology and rocks, and trying to figure out what to expect when I get out there this summer. And we're going to do some other analyses. When the fault ruptures, you get a fault scarp, which is vertical generally. And over time, it erodes and sediment sort of piles out in front of it. And that's called a colluvial wedge. And in that pile of sediment, you get carbon-14 in charcoal. So forest fires happen, charcoal rains down and fills up in the soil. And if you dig down in the soil, you can pick up these charcoals, and that gives you an age for that soil horizon. And you can go through the stratigraphy and get a whole series of those, and that'll give you sort of a bracketing age for the most recent earthquake. And we're going to use cosmogenic isotopes, helium-3, which is formed from cosmic rays bombarding minerals in the rock. These are all igneous rocks, lots of basalts and basaltic andesites and such like that. And we're going to use that. That gives us an age for how long that boulder has been sitting at the surface, which will give us an approximate age for these glacial features. I actually might be able to get, I hope I'll be able to get 2 papers written out of this, one for the earthquake history and one for the glacial chronology, because that's never been done in this area.
Fantastic. And that brings us right to our 1 o'clock hour. If anyone has any more questions for Andrew or questions that didn't get answered, and Denny, I see you've got one, stick around for the social hour afterwards if Andrew's still here, and maybe there's some other conversations that we can have. In fact, we might even take some of those into a breakout room. It's 1 o'clock. We're going to shift now. And thank you, Andrew, for that very thorough and fascinating exploration of earthquakes and volcanoes. And we're really looking forward to hearing about your research as it progresses. We're going to shift to talking about what we've learned from, or what we're thinking about earthquake preparedness. I think I'm going to have Carol turn off the recording at this point, because you're going to invite people to have a more casual conversation about, your own experience and whether you're going to buy a generator or not, and things like that. And I don't want people to feel intimidated